Okay, so then we're gonna start today on forces and defining forces and understanding how the AP exam wants you to deal with forces, because it seems so simple, right? But it's much more nuanced than that. So let's just do some of these concept checks first, because these are very interesting questions that I think students may miss here and there. So let's go through and discuss some of these. So number one, true or false? Do you think it's possible for inanimate objects like tables and chairs to exert a force? What do you think?
I think it's true if they're moving.
Only if they're moving?
Well, if they're not moving too, because like gravitational force or force of gravity.
Force of gravity is caused by the Earth.
Oh.
You're on the right track, though. It is true. Does anybody know why it's true? Because they can't move by themselves, right? They're going to just sit there.
There's a normal force.
Normal force, right? So when something sits down on it, they push back. And it's not like they develop brains and push back on it. So that one's true. We're going to say Fn for normal force. Good. 2, inertia is the force that slows an object down. True or false?
False.
False. Why?
Inertia is the resistance of an object that's like in motion. It wants to continue being in motion. If it's not, it doesn't want to move.
Yeah, a resistance of movement, we want to say, right? And we can't use the word force to motion. Or change in motion, I guess we should say, resistance to change in motion, right? Because if something's moving, it doesn't want to change. If it's something is still, it's not going to want to move. 3, an object can move even if no force acts on it.
False?
False. Wait, true. No, it's true. So here's the confusing idea in a lot of these physics questions. Maybe something pushed it like 5 minutes ago, right? So there was a force applied to it at one point, but once that force is removed, there's no force acting on that object, right? If I launch something into space, if anybody watched Gravity, right? Sandra Bullock's just kind of spinning in space, even though no force is acting on her. 4, friction is the force that slows object down.
True.
It doesn't just slow objects down, unfortunately. What is the definition of friction? Friction is the force that opposes the motion. So it is quite possible that friction speeds you up, and we'll get to an example later. Friction actually can speed you up. Number 5, when I push a cart, it will roll but slow down as the force is used up. What'd you say, Bronson?
F.
F, why F?
Because it should move at the first.
Something's wrong with your mic. It sounds like you're a robot. I don't know if you have headphones or something. But I'll explain. When you push it, you can't use force up. Force is not like water or something, right? As the energy is transferred, maybe you can't use force up. And then this is also assuming like if there's no friction, right? Technically in our world, in AP Physics 1 world, it's going to keep moving, right? If you push a car, it's just going to keep rolling forever. Six, if a race car is going faster than the school bus, the race car must have a greater force acting upon it. Anybody?
False.
False. Can you explain? I know these are so hard, right? Because what do we know about force, right? Force is the component of mass times acceleration. So maybe the race car has a little tiny mass, right? If it has a little tiny mass, it doesn't need as much force to accelerate it, right? So it's going to depend on both the mass and the force. So if it's a behemoth school bus, it'll take a lot of force to move it. Number 7, when I stand still on the ground, I stay on the ground because the down force of weight on me is greater than the force of the floor on me.
True.
False.
False. It's not greater, it's equal. Yeah. If the downward force were greater than the upward force on the floor on me, then we'd fall through the floor. And that happens, right? But hopefully not soon. Number 8, if an object is moving when all forces on it cease, the object will slow down and stop.
False.
False, right? We're in this perfect physics world where there's no friction. Number 9, the inertia forces it to keep going with the same motion.
True.
True. The only thing that I want to keep in mind here is like, I don't like the word forces right then, because that confuses it with the idea of force. So maybe like compels or maintains the same direction of motion. I just don't like the word force. Number 10, if the leftward force of an object is stronger than the rightward force, the object moves to the left.
True.
Explain.
Similar to if like normal force was less than gravitational force. So
You'd fall
basically, if the leftward force is more than it, whatever counteracts with the rightward force would push it to the left.
You'd think, right? So you're true, you're 50% true. This one's false. And here's why. Imagine that I'm going this way, right? I'm going to the right with some sort of velocity and I'm in my car. And then I slam on the brakes, right? When I slam on the brakes, my leftward force is bigger than my rightward force. But have I started moving to the left yet? Not right away. Like if I slam on my brakes long enough and I keep compelling the force, I can change direction, but not right away. So this one's a nuanced question. So it's a yes and a no. It will eventually possibly move to the left, but not right away. Does that make sense? If a car moves forward because of the forward force of the car's engine.
False.
This one's false. Do you know why it's false?
I think I kind of remember it has something to do with the wheel. I
Mhm.
don't think it was torque, but it was something tangent to the wheel causes it to roll forward.
Yes, you're right. The force of the friction on the wheels. The engine causes the wheels to turn, and the force of the friction against the ground. The tangential frictional force on the ground. And this is the same thing as, where was it earlier? Oh, shoot. Oh, the friction slowing the object down, right? This is an example of friction speeding something up. Number 12, an object can stand still and yet have forces acting on it.
True.
Easy, right? We're doing it right now. Normal force, force of gravity, boom, boom. 13, an object can have a force acting on it and yet keep going the same speed.
Would that be true?
This one's so trickily worded. What are you thinking, Bronson, when you say true?
So say it's like a car that has force acting on it the other way, it could increase the force in the other direction to keep the speed.
Yeah, and so the way you explained it makes sense, but the way you explained it relies on two forces, right? You increase one force and therefore a contrasting force increases as well. And so that's why I don't like the wording of this question. It says a friction can have a force acting on it. Can an object have one force acting on it and keep going the same speed? No. Two forces, yes, right? They equal each other out. Number 14, if an object moves to the right, then it must have a force to the right acting on it.
Would that be true?
This was the one earlier when we said, what was it? It was related to number 3, right? I was saying number 3 is like maybe 5 minutes ago I pushed it, but that force isn't acting on the object anymore, right? So I pushed it 5 minutes ago and it keeps moving to the right, but there's no force acting on it anymore. How would I type that? Old force. Force to start movement, right? But no longer there. What about number 15? It's possible to exert a force on an object without touching the object.
True.
Sounds true. Any examples you can think of?
Gravity.
Gravity?
Normal force. Well,
No, normal
guess
force
it-
has to touch.
yeah.
And then there's like silly ones, like if you really want to like, I don't know, use a fan, right? Or magnets, if you ever take electricity and magnetism, magnets can move something without touching it. But gravity is the easiest example. Now we know the answer for 16, right? Friction can cause an object to speed up. True. Car wheels. Number 17, heavier objects have more gravitational force acting upon them.
True.
True, right? F is equal to mg. Right? If they're heavier, that means they're more massive, and therefore force is going up. True. An object has two forces acting up on it, an up and down equal force. This object can move horizontally.
Could this be true if the object had like an old force acting on it?
That's the same idea, right? I pushed it a second ago and it's just like boom, 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 right? And this is normal force and this is the gravitational force, right? And it's not doing anything vertically, but it can move horizontally. Exactly right, sir. Number 19, heavier objects fall at a greater rate than lighter objects. We're gonna neglect air resistance here. No air resistance, true or false?
False.
False, right? This is the Galileo experiment. We're not going to care about surface area that we talked about last time. We're not going to care about like how like dense or how light it is. In the absence of air resistance, everything falls with the same rate. And then number 20, in a tug of war, the team that wins is the team that pulls on the rope with more force.
True.
Explain.
Their force makes it's greater than the other team, so then it moves the middle point to the other side.
I believe you, but your answer is only partially true. How else could you win tug of war? Anybody play tug of war recently? Because it depends on what your grip strength, right? Holding onto the cord. Right? What if the one team pulls and the other team technically like lets go by accident or loses friction? So it doesn't necessarily have to do with pulling, right? Or what if like friction causes them to fall over, right? So there's, you're not that you're wrong, right? But there's a bunch of other scenarios that doesn't make this 100% true. And remember, a lot of times on these true false questions, they're like, it needs to be true 100% of the time. So your answer isn't wrong. It's just not 100% true. Friction. Okay. So please keep a lot of these in mind, right? Because these are really common misconceptions when people are thinking about force, right? The force doesn't have to be currently acting on the object. The force, a rightward force doesn't mean that your object moves right. A leftward force doesn't mean that your object moves left, right? And you can have vertical forces and have things moving horizontally, or you can have horizontal forces and have things moving vertically. Right, so these are the concepts that you do need to know when you're trying to explain something, and be careful with your wording, right? I'm being really picky with the wording here because the graders are picky with your wording too. And then I think y'all should be familiar with doing some of these, right? These are just free body diagrams. So I'm not going to spend too much time on that. Although I do want to just go over the different types, right? So these are the types of contact forces. You have the weight force or the gravity force, right? Normal force, tension, friction, drag or air resistance, synonyms, right? And any other applied force. So that would be like the engine or me pushing something. And so on some of them, just remember when they want the free body diagram, they do not want you to break it up into components. So for example, number 3, right? You just would draw this, you would draw this. These would be labeled tension, right? So you could use capital T or F sub capital T. The one thing that they want to be very picky of is they want you to make sure you're drawing the arrows with the right length or the right magnitude so that they look balanced. They're not going to be super picky, but if I drew my like downward force like this, that probably wouldn't be enough, right? They want to make sure that the downward force is equal to the 2 upward forces here. So I have to make this just a little bit longer. I can do FG or MG. So they do care about the size of the arrows when they ask for a free body diagram. What about number 5? Where should we draw arrows here?
Probably in all 4 directions, but like for the like they should be equal for the vertical arrows, but also for the horizontal because the car's at constant speed.
So if you have an upward and downward, FG is downward, right? FN is upward. These should be equal, right? And so what are you saying we should draw to the left and to the right?
Equal forces.
Well, what are those forces? Right, we have these forces up here.
Wouldn't the forces to the left be like air resistance and friction, and then the force to the right would be applied force?
Sure, that's possible, right? So you could have F air and F, and then you could have F applied to the right. Absolutely, and make sure, did you say you want your arrows to be equal or unequal?
Equal.
You want them to be equal, right? Because constant speed means no net force. So that would be true if in your case, you're saying air resistance and friction. However, in other cases, there may be no air resistance or friction too. So maybe in a different scenario, it's just these two. So depending on what the question asks, right? It's either the top one or the bottom one. So I'll say this is 5A and I'll say this is 5B. Both are correct. And I want to make sure that the sum of these arrows are equal to the length of the one pointing forward. So good. What about number 11?
They would all have gravitational force.
Are the arrows the same size or different size?
It'd be the same.
All the arrows should have the same gravitational force because gravity technically hasn't changed and their masses haven't changed. Are there any other arrows I need to draw, Tiffany?
If there was like if you threw the ball, which I guess this would, there'd be a horizontal force to the right that's applied, and then a drag to the left.
Ah, so this is one of those examples. If I threw the ball or I kicked the ball, this is me like I apply the force at the beginning, but as soon as I let go, there's no more force on the ball. So this would be an example of there's no horizontal force. Technically there is drag, but let's just pretend there's no drag here. We're going to say no air resistance. So that's a really hard concept to understand, right? Because it's like the ball's moving to the right, there must be a force acting on it. And I would say most of the time on the test, there's actually no force acting on it. So this is literally it, just 3 vectors, each one down, 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 the end. Okay, and then this is a spin-off of number 5, right? If the car's slowing down, we're going to use Bobby's example where there are forces to the left, right? Here we'd want to make sure the leftward force of friction and drag are going to be greater than the one on the right, which is the applied, because that's what's causing it to slow down. Obviously, you have Fn and Fg. And then in example 13, then we want to make sure the applied force is bigger on the right to show that it's speeding up, right? So this is a little FF and a little FD for drag, right? And then FG, Fn, okay? So the key component you're going to see here a lot on the test is constant speed, right? So constant speed means the arrows that are parallel to your direction of motion need to be equal and opposite, right? So here we have down, mg, right? Don't break it up into its components. We have the F applied here. Oops. If we have this F applied, if it's constant speed, then something needs to be pulling down. Well, technically there is this component of gravity pulling down, so we don't need to do another one, or maybe there is a friction. I don't know if there's a friction or not. Okay, question mark. It has to depend on the question, and then there's going to be Fn, right? And the normal force is always going to be perpendicular to your surface. They do not want you to break up into components, so you could do it off at the side for your own reference. Same thing over here, right? We have an applied force here by my finger. Anytime I push against the surface, that surface is going to push back. So this one's going to have a normal force. Otherwise, the wall would break. And then we have mg. And then for shear, here, since I'm pushing it so hard and because it's held at rest, there has to be something pushing up, right? So then that would be the force due to friction. That one's a common one that's not so obvious. Man and a bicycle go over a hill at a constant speed, right? So constant speed, this is going to be your mg, right? Or your fg. This is going to be your fn. And since it says constant speed, right, that means either the right or the left have to cancel out, or maybe in this case, there are no left or right ones. I don't know, right? The question doesn't give me enough information. So I'm just going to leave it like that. And 28 is the satellite is orbiting Earth, right? So how many arrows should be in this one?
Wouldn't there be some kind of like centripetal force that's like acting towards the left of where the satellite is right now?
You are correct. What do you think is contributing to that centripetal force?
Friction.
Friction, a satellite, somehow the Earth, remember friction is a contact force. Two things have to be touching each other.
Oh,
Satellite. This is a non-contact force that Tiffany so
oh,
gracefully.
so gravity?
Gravitational force, right? Just the one force due to gravity here. And you said pointing to the left. Not that you're wrong, but I do want to say when you're talking about centripetal force, make sure you say pointing towards the center of the orbit or something, pointing towards the center of the circle. Because maybe a second later it won't be to the left and to the right. Okay, good. We'll talk more about centripetal next time, but we're going to focus mostly on just understanding the idea of force. So what is force, please? It's MA. No, it is, but a push or pull resulting from the interaction between two or more objects. Right, so the Earth on the satellite, the Earth is pulling the satellite with gravity, right? The wheel on the road, the wheel is pushing or pulling the road to move forward, right? So any kind of things where two things either contact or affect each other can result in a force. So what's an example of force that you've experienced continuously all your life?
Gravitational force.
You've experienced that one, unless you've been to the moon or something, and then you can say the lack of gravitation. But even then you get the gravity of the moon. How about a situation of an object where it's given a force, but it doesn't move? You're like pushing something and it's like, oh, it's not moving. Pulling something and it's not moving.
Could it be like you're pushing a wall?
Pushing a wall. So then what would we say the F applied here would always be less than or equal to the normal force, right? How about something that's not stationary? Like if I go outside and start like pushing on this like gigantic boulder or something, I'm like, come on, boulder, move.
The frictional force would be greater.
What kind of friction?
opposing?
Remember, there's two types of frictions. We're going to get to them in a second, but what are the two types? If something is not going to move, it's where the static friction force is greater than your applied force. Right? Because technically, if you just say friction, I don't know if in grading they would like give you full credit. Depends on the question, I guess. Right? You have to say the static frictional force doesn't overcome. And then this is for the experimental questions. What object would we use to measure force? You can use a spring scale sometimes. Right? That's where you like have a thing and you literally can see how many newtons of force it's pulling. Right? So in case you ever have to design an experiment using force, you can just talk about a spring scale to measure different amounts of force. Okay, so what is Newton's first law? That one should be easy, right? For every action. No, sorry, that's number 3. Oh my gosh, that's confusing it. What's law number 1? The law of quote unquote inertia, even though we don't say that. Objects in motion, at rest, stay at rest. Objects in motion, stay in motion, unless what?
Is it acted upon?
Acted upon by some what?
Is it opposing force?
We're going to use the word external force. This is going to be really important when you're answering, because like if I'm in a closed system and I start like punching the walls and stuff, nothing's going to move because I'm an internal force, right? But if I'm stuck inside some elevator and then somebody else comes and like takes a like a what's that called, a wrecking ball, and knocks it into the elevator, then it's going to finally move because that wrecking ball is an external force. What does the term net force mean? That's just all the forces added up, right? So we're gonna, actually we should say here some external net force just to like clarify here. So it's just, net force is just all the forces added up. Because it is possible to be acted upon by external forces that cancel out, right? If they cancel out, then I'm still not gonna move. And then Tiffany gave us a good definition of inertia earlier, right? Inertia is just the tendency of an object to want to stay in motion, right? Or the tendency of an object at rest to want to stay at rest. So we'll go with that definition. And then this inertial reference frame is kind of like what we talked about last time, is where you're looking from. So it can be either still or with constant velocity. This is the idea of me like, oh, standing at the side of a river and watching a boat go by. Well, the boat looks like it's moving, right? That's my inertial reference frame. It's making it look like the boat's moving. But maybe I'm in the boat all of a sudden, right? Now I have a constant velocity. I'm like, well, the boat's not moving. Everything else is going backwards. So your inertial reference frame is basically where the idea is coming from, where the point of view is coming from. Okay, so give 2 definitions of mass. The first one you learn in like science class in like middle school or whatever is the amount of substance in something, right? The amount of stuff. Right? And in physics, the amount of stuff in something is equal to the gravitational mass. If I take a bag, right, and stick a bunch of rocks in it, it's going to have more mass because there's more stuff. If I stick feathers in it, right, there's not as many atoms technically, or the atoms are less dense. That's one definition of mass. And then the one we just kind of talked about is inertia, right? We can use inertia to define mass. So mass could be the object's resistance to acceleration. So that'd be definition number 2. We can say motion or acceleration. And that should make sense from our physical perspective, right? It's really easy to like flick a rock, a tiny rock, right? It's going to go flying versus if I have a gigantic boulder, it's going to resist my motion because it has more mass. And then what units do we use? Kilograms, obviously. Okay. Any questions on that? Okay, so we're on to the second law, right? So we definitely know the second law. You've used it a million times by now, right? So it's sigma F is equal to mass times acceleration. And what does the sigma mean?
Total.
Total, sum, right? Sigma is literally the Greek letter S. Sum up all the forces. And then I'm going to add a caveat here, right? In one direction, right? We cannot add up the vertical and horizontal forces. We cannot add up perpendicular forces. That's not going to work for any of our acceleration or any of our problems. Yeah, so that's the easy part. Now, how the heck are we going to write it in a sentence? Because sometimes they may need you to explain it. What is Newton's second law in a complete sentence? And don't say mass times acceleration. In objects, acceleration is the result of the net force on the object divided by the object's mass. Another way we can say it instead of saying divided by, right, is the result of the ratio of the net force to the object's mass. Or we can use ratio or divided by. And we have to use the word result here, right? Because the idea is that if I push something with a force, then it results in the acceleration. So that goes to the part 1 then, right? A net or unbalanced forces causes acceleration. Right, and then you should know this part by now, right? We measure forces in newtons. And then we have the third one, right? Third one's pretty easy. For every action in nature, we're going to say, on Earth, basically. We're following Earth physics, I guess. There is an equal and opposite reaction. So what is this action that we're talking about? This action, we're going to use this force, right? That's what it means when we say that. So for every force, there's an equal and opposite reaction. So that reaction is called a reactive force. So those are for your reference, right? So you can, instead of saying action when you're doing your explanations, you should be saying equal force and reactive force, or applied force and reactive force. And then what's the important thing to remember about these action and reaction forces? What do you need? Pencil or pen? Anybody know this? It's that the action and reaction forces are acting on different objects. They cannot be applied to the same object. Right, simple one here, right? When you stand on the floor, you are exerting a downward force on the floor, right? So that's you. This is the force of you, comma, floor, right? So that's the action force, right? And the reaction force would be the equal and opposite, right? That would be the force of the floor on you. Feel your feet right now, right? You don't feel anything going down on your feet. You feel the floor pushing up on your feet. So you feel the reaction force, and then the floor is feeling your feet pushing down on it. This one's a hard one for people to understand too, right? So you feel the earth pulling down on you with gravity, right? And guess what the earth feels? This is so illogical. The earth feels you. This is, you have a gravitational force too. The gravity of you. Do you not have a stylus? That makes sense. Okay, so let's do this action and reaction force then. So we have this pretty picture here of you pushing a desk across the floor. So there are 4 forces acting on the person. There are 4 forces acting on the desk. So I'll do the easy ones and you have to help me do the hard one, right? Both the person and the desk have an mg and an fn, easy peasy. And they should be equal in size, right? So you tell me, what are the left and right forces acting on the person? Anybody?
Wouldn't the force, like, if the person is putting an applied force on the desk, wouldn't that mean the desk is kind of technically applying a force on the person towards the left?
Correct. So on the person, there should be on the left, right? There should be the force of the desk, right? So that technically means that on the desk feels the force of the person. And then when you're labeling, right, you can do person, comma, desk. This is the person on the desk. That's usually the order you do it, right? And then this one would be the desk on the person. Great. So then what the heck are the other 2 forces then? I have these 2 arrows here that are blank.
Would the other one on the person just be applied force and then the one on the desk be friction?
I agree with this one, though, right? Somehow the desk is moving forward, so it's going to have some sort of friction or resistance backwards, right? But then applied forces, that means something's applying to the person, right? Nothing's pushing the person forward. The person is applying a force, but there is no force being applied on the person, right? We think about the person, think about yourself pushing the desk, right? What do you feel on you? Okay, well, I feel something on my feet. That's the normal force. Gravity's pulling down on me. I don't feel anything behind me here. Do I feel anything else as I'm going forward? Anywhere on my body?
Would it also be friction?
I feel it on my feet, right? There's friction on my feet. I'm not only pushing down, but when I push forward, right, there's the friction that allows my feet to not slip. My feet want to go back, right? My feet want to go this way, but the thing that's keeping my feet from going back is friction. So friction is actually pushing me forward. Very confusing, right? And then once you understand that, then it becomes pretty easy, right? If it's speeding up, then the right arrows become bigger than the left arrows. If it's slowing down, then the left arrows are bigger than the right arrows, right? And if it's constant speed, the right and the left arrows are equal size. So I'm not going to worry too much about that. It's that whole labeling part that can be confusing. Now, in that picture, which two horizontal forces must be the same strength at all time, though? This one's Newton's third law, right? The F of the desk on the person must equal the F of the person on the desk, right? That's the equal and opposite. I can feel a different amount of force than the table feels, right? Because we have different masses, we have different weights. So we cannot say that these frictions are the same, but the equal and opposite forces must be the same. And then when it says explain your reasoning, you just write a sentence saying that, right? Referencing Newton's third law. Any questions on that? Okay. So let's apply it in an FRQ style question. So we have the Hulk, right? And then we have a baby. For some reason, they're playing tug of war with each other. They hate each other or something, right? And obviously the Hulk wins. And then the four students try to explain it. So student one says the Hulk wins because the leftward force on Hulk is less than the rightward force on Hulk. Student two says Hulk wins because the leftward force on Hulk is less than the rightward force on Leroy. Hulk wins because the leftward force on Leroy is less than the rightward force on Leroy. Hulk wins because the leftward external force on the Hulk-Leroy system is less than the rightward external force on the Hulk-Leroy system. So again, this is a very similar idea, right? So if we do the FBD, right, this is mg. Actually, I should make this small, right, because it's a baby. So tiny mg for baby, tiny fn for baby, big mg for Hulk. I'll capitalize it too. So big fn for Hulk. Okay, now there's going to be a rightward and leftward force. And this time I'm going to care about the arrow size. What do you think?
Maybe there should be like a really large right arrow on the baby and a very small left arrow for the Hulk.
Okay, does everybody agree with that? A large right arrow on the baby, a small leftward arrow on Hulk. What would be causing your arrows, Bobby?
Is there such thing as like pulling force, or like could we just say applied force?
Pulling force, you're on the right track. Look, they have a rope that they're pulling. What happens when you're
Oh,
pulling?
tension.
Tension. Okay, and we're assuming that the baby has an iron grip, right? We know the Hulk does. The baby also has an iron grip. It like is a rock climbing baby. So tension. What can you tell me about tension in a single rope, right? That rope is considered one system. Would it make sense for like the left side of the rope to have more tension than the right side of the rope? Because it's all a singular rope, it's supposed to be the same size arrow, right? It's one rope. If we had two different ropes, then we can't say that. So technically here, the arrows coming out of these ones should be equal and opposite. This is how the test is gonna like throw you off, right? They do this with the gravity thing. Oh my God, the earth is so big, so the earth must pull me with more gravity than I pull on the earth. But no, this is equal and opposite. It's that same rope. So the amount that the Hulk is pulling is gonna be equal to the amount the baby is pulling, assuming the baby doesn't let go. So then these forces cancel out. So then there must be another set of arrows somehow, right?
Would it be friction pulling outward for both?
Friction pulling outward. Are these ones the same size?
No, those should be different.
These ones should be different, right? Which one?
The baby should be less than the Hulk.
Exactly. The baby should be less than the Hulk. That's why it loses. The baby loses not because it has bad grip strength here, because it cannot gain or like include enough friction. So this goes back to the tug of war question we had earlier, right? So it's not necessarily because he pulled with more force, it's because the friction thing. Okay, so now take a second and look at these and see which of these four do you think is true. They're all like, some of them are partially correct. Anybody?
Wouldn't students 1, 3, and 4 be correct? But not student 2.
I agree, right? So this is the outward system, right? So with this a crazy outward system thing, I try to think, okay, well, if this is one system, right, I'm going to draw a box around the system, right? And so the only outward two forces are this one and this one, right? So that's why student 4 is correct. And so for you, right, I'm not going to worry about the whole writing a paragraph. But basically you'd want to like put them all together into a single paragraph and being like, okay, these are all true. The tensions must be equal, however, right? And then blah, blah, blah. And then you can combine them in a single paragraph. Any questions on that one? Cool. Okay. Next one is asking for the equation for the force of weight in an object. That one's easy, right? The force of weight, W, is just equal to mg. And then we have the idea of a contact force. So we're kind of talking about this earlier, right? You can have a force without contact, so that'd be like gravity, right? But a contact force is any force that results in two things physically touching each other. So what are some examples of physical contact forces?
Normal force, friction.
Normal force, friction, keep going.
Applied force.
Could be. The thing with applied is applied may not be too, right? It can be an engine or something that doesn't touch anything, technically.
Would tension also be?
Tension is a contact because you can't have tension without things touching each other, right? So, and then, so list goes on, right? You can have other contact forces, air resistance technically because you're contacting the air also, but it's just the idea of two things touching each other. And then we also have the idea of inertial mass and gravitational mass. We just defined them earlier, right? So gravitational mass is the amount of stuff in something. This is the stuff definition, right? And then the inertial mass, that's the resistance to motion. And then for your understanding, the AP test might use either one of them, and inertial mass and gravitational mass have been proven to be the same on Earth. Okay, the amount of inertial mass and the amount of gravitational mass is the same. So that's why, and I'm jumping ahead a couple chapters, but that's why we have this equation here, which is what G M1 M2 over R squared is equal to mg, right? That's why this is true. This one's the gravitational mass. This one's the inertial mass formula. If we wanted to do a simple experiment, what do we need? Well, we need something to measure the gravitational mass, right? So that'd be any kind of scale, something to weigh something. What else could we use, right? A thing that measures gravity that you should have learned from a different chapter is maybe like a pendulum, right? The pendulum would measure inertial mass, right? Because that's the resistance to motion, right? Because it's like, okay, it's going to slow down and swing in the other direction, right? Swing in the other direction. So scale for the gravitational mass. And then we're going to use a pendulum for the inertial mass. So maybe that'd be a different way of you thinking about it. Inertial is spring, something swinging back and forth. Pendulum just straight down. Okay. And then earlier, we also talked about the whole idea of like static friction, which is when things are not moving. And so we have kinetic friction, right? Kinetic friction opposes motion when an object is moving against another surface. And I'll put maybe rough in quotations, right? Because sometimes they'll say smooth or sometimes they'll say ice, right? As soon as they say smooth or ice, then it doesn't work anymore. So what is frictional force proportional to? They're going to use this phrase so much on the AP physics test, proportional to, like, well, you all know the equation, right? Well, FF is equal to mu K Fn, right? I'm sure you know that. Proportional to means, well, if I have the equation y is equal to kx, I can say here that y is proportional to x, assuming that k is not changing. So in this case, what is the frictional force proportional to? Well, this mu k is constant, so it's proportional to the normal force. We can do it with the other equation we were just talking about earlier too, right? We did W is equal to mg. Well, what is weight proportional to? It's proportional to the mass on Earth, right? Because gravity is the same. This one stays the same on Earth. So proportional to is when you have some sort of linear equation like this, right? Y equals mx, no b, there's no mx plus b, right? Just mx, y equals kx. So then we have ff is equal to mu k n. I'll just do n because I don't have enough space here. And then the answer for this part is normal force. The mu k stands for the coefficient of kinetic friction, right? And what does the mu k depend on? What are the numbers that mu k can be between?
0 and 1.
0 and 1, right? And so it's going to depend on how rough the surface is, right? But obviously that's not going to be sufficient enough for the physics test, right? So we need to say the interaction between the molecules of the surface and the object. That's the funky definition of friction, right? Friction is because when you rub things together, the molecules kind of like have these intermolecular forces, and they like pull a little bit and they snag a little bit, right? In the jaggedness of my hands, there's all these, if I had a microscope, you could see all these little tiny things in the surface of my hand, right? And then they cause all these intermolecular forces that create friction. And then we have static, right? Static is not moving. So what is static friction? The amount of force required to overcome movement or lack of movement. I guess inertia, right? Inertia. Can't use the word inertia though. It's the same equation, right? So it's just F is equal to mu SFN. And then mu S is the coefficient of static friction. If you look on the AP physics review sheet, you're gonna see that F is less than or equal to mu absolute value of Fn. I think that's what it looks like on the equation. See, why is there a less than or equal sign? So in a lot of ways, the frictional force is a reactive force, right? So when I push something and it's not moving, right? If I push it with 2 newtons of force, it's going to push back with 2 newtons of force also. But is that the amount of force required to overcome motion? No, right? It's 2, right? But maybe I push with 3 now. I'm pushing harder with 3. It's still not moving. But as soon as I push maybe with 10, right, then I start moving it. So the force of friction is going to actually depend on how much I'm pushing on it. So I can keep pushing on it until I hit that magic value. Once I hit that magic value, it's going to start moving. Right? So the force of friction is not always going to equal mu Fn for static friction. It's everything up to that magic number. Does that make sense what I just said? Okay, so that's why there's a less than. So how do we write in a word static friction? Will be less than mu s Fn if the object doesn't move. Cool. Questions on that? Okay. Another really common question, they're going to ask you to read a graph and translate it. We kind of tried to do this last time, right? So if we draw the forces acting on the student, what do we have? There's no left or right this time, right? Because the student's standing exactly still in an elevator. We have mg pointing down. And then we have Fn pointing up. Now, what does this scale reading tell us, right? They're measuring the scale reading on the elevator over a bunch of seconds. Does this scale reading link to the Fn or the mg?
mg.
It actually relates to the Fn. So anytime you step on a scale, the scale is measuring how much it's pushing back up on your feet. So it's measuring the normal force. mg is always going to be a constant value on Earth. You're always going to have the same weight. If you weigh 100 kilograms and you weigh 980 newtons, mg will always stay the same. But when you're going up and down an elevator or something, the normal force will differ depending on which direction you're going. So this scale reading is the same as Fn. I'm just going to put these arrows to indicate my positive and negative direction, right? And so if I wanted to do my sigma equation, it'd be sigma of F is just equal to Fn minus mg. And that's going to equal the product of the mass of the system and the acceleration of the system. So then this will allow me to solve for Fn then, right? So my normal force is going to equal ma plus mg. I have enough information to plug in a little bit of information, right? So I know that the student weighs 50 kilograms. I know that gravity is 98. So I can even go a step further and say Fn is going to equal, well, there's only the mass of the student, right? So 50A plus what is mg here? It's 490. So this is the full equation for my scale reading. So then from that point, I can find the acceleration, right? So the acceleration at time t equals 7. Well, if I go to t equals 7 here, what do I see? I see that the scale reading is approximately what? I don't know, 5, 510, 520, 530, right? So we say 530 is equal to 50A plus 490. 40 is equal to 50A. So then A is equal to 4 over 5 meters per second squared. And it's positive, right? Remember, it's an acceleration. So we either need to write the sign, or we don't need to write the sign because it's positive, or indicate direction, right? Indicate direction for vectors. So what is that telling us? That's telling us when the elevator is going up, you look heavier. And I'm sure you can recreate that in your mind, right? When you're going up the elevator, you feel like you're pushing against the ground more, right? It's like, and then what about this one? T equals 63, right? 63, same thing, but in reverse, we go down. What do we get? It looks like maybe it's about 445 equals 50A plus 490. If we minus it over, it becomes negative 45 is equal to 50A. So then A is negative 0.9 meters per second squared. So what does that tell us here? That tells us my elevator is going down. Right? And so when my elevator is going down, I look to be lighter. Questions on that one? Okay. So now this is the physics part, which you'll see on a free response question. Explain how the data can be used to determine the top speed of the elevator's motion. Any thoughts there? So we have this force graph over time. Explain how we can use the graph to determine the top speed of the elevator's motion. Anybody have any thoughts here?
Would the max speed be 0.9 meters per second squared?
No. How do you get that?
With acceleration?
The acceleration, the max acceleration, right? If we want to maximize it. Okay. So remember, how does speed relate to acceleration? Well, remember that speed is the absolute value of velocity, right? And then what is velocity? Well, velocity is related to acceleration, isn't it? Remember last time when we looked at acceleration, velocity was the area under the acceleration graph. Remember that part? If we have an acceleration graph, then we can use it to find the velocity. And then from there, we can figure out what's going on. So if I wanted to find our acceleration graph, well, we kind of have that information right now, right? We can literally, we know at the beginning that this is 0, right? We can change our scale of the graph maybe. We can change this to 0, right? We know this acceleration, we know that this is 0.8. And we know this one down here, right? We know that this one is negative 0.9, right? And then we can just make the dots here, connect the dots, pretend it's an acceleration graph now. if we pretend it's an acceleration graph, what can we do? We can take the area under the curve and then make it positive to calculate the speed. Do we have to do it? No, it doesn't say we have to, right? It just says explain how to do it. Right, so we'd replace the values on the graph, calculate the area under the curve for velocity, and then make it positive to find the maximum speed. Does that question make sense? And this is going to be a thing on the AP Physics test, right? It's not even do any calculations, just explain how you would do it. Good? Okay. Seems so simple. It's like, oh, we're just measuring things moving up and down, but it can be kind of complicated. We shall move on to things at an angle. So they may or may not use the word oblique angle, so don't get freaked out about it. Oblique just means it's not parallel, not perpendicular, right? And so this is where we're going to start making components or right triangles, right? So forces that are perpendicular to the motion vector, or we can say the acceleration vector. If they're perpendicular to the acceleration, they will not do work. Right? If I'm moving left and right, this thing is not going to change this motion. Forces that are parallel to the acceleration will do work or will contribute to the force or will contribute to acceleration, right? So we can say will do work. But if the force is opposite to the direction of motion, right, to the motion, we will count that force as negative. So just to break this apart, right? Earlier we did the free body diagrams. I'm not going to do the free body diagram. I'm just going to review the component form, right? So here we have mg. If we're going to do the free body diagram, we'd stop there, right? But then here, since I just want to break it up into components, I break it up this way, right? Since this is theta, geometrically this is theta. The one that's always opposite is going to be the hypotenuse times sine theta. Opposite is always the sine. And then the adjacent is always the mg cosine. We're going to assume that there's friction in the first one. So it says this is Fn here, right? I do not need to draw this down arrow here if it's down here. Or I can draw it and just label it mg sine theta. Right, that's my downward force. And then I have an upward force to the ramp too. I probably want to pay attention to make sure it's shorter than the first one, right? Unless it says constant speed. If it said constant speed, we want the same one. Right, and this would be, we could either call it FF, or if we remember the formula, it's mu, technically Fn, right? But here on the ramp, Fn is equal to mg cosine theta because they're equal and opposite. So we just call this mu mg cosine theta. You can call it any one of those things. We can just call it mu Fn also, if you're better with that one. I want to make sure you're comfortable with this version because this one is super common. Right? You shouldn't spend too much time setting this up. If you're struggling with this, make sure you review how to break this up. this one here, right? So this one again is mg. This one again is Fn. We have some, I'm going to pretend this is a rope. Okay, so I'm going to call this T, right? So if this is theta, we break it apart this way. This is T cosine theta because it's adjacent. This one's T sine theta because it's opposite. Same thing over here. So we see, look at this. This is like this motion graphic thing, right? So it's showing that there is some acceleration to the right. So what do we have? We have this T here. Now, if we draw from the center of motion, now this T is not T cosine theta. This one's T sine theta because it's opposite from the angle we're given, right? If we break it up this way, this is T cosine theta. And then we're assuming maybe it's on the ground. So mg and then Fn. It says assume no friction on this one, so I will not draw the friction vector here. Cool. So that should be pretty much review, hopefully. So then let's fill this part out. When the object is not on an inclined plane, the blank force is the one that makes the oblique angle. This is the FG force, right? That's the one that we need to split up. So you can use the picture from earlier if you want, with or without the friction. But the normal force on the block is Fn is always going to equal mg cosine theta. Same thing for this one. The acceleration of the block. So from the picture above, if we want to sum up all the forces, right? We have the mg pointing down and we have the mu mg pointing up. So it doesn't matter which direction we make positive. So I'll just make the downward motion positive, right? So if I want to sum up the forces here, the one pointing down would be mg sine theta. The one pointing against the direction of motion is going to be mu mg cosine theta. Right, that's because the force of friction is mu Fn. And then from Newton's second law, we know that that's equal to ma, right? So if we wanted to solve for acceleration, look at this, all the m's cancel out, right? So in this case, a is equal to g sine theta minus mu cosine theta. And of course, I took this one and I put it on the wrong side. So luckily, I'm using notability and I can just move it over. This is the one with friction. So if there were no friction, this one would just be F is just mg sine theta, right? So there's no upward friction force, right? It's just the mg sine theta pointing down. This one's mg sine theta. This one's with the mu mg cosine theta. In this case, this is also equal to ma. And then here we can, again, cancel the m's out, right? So here a is just equal to g sine theta. So in both situations, what conclusion can we draw? We can draw that the mass doesn't matter. Anytime you cancel it out, we can say the acceleration does not depend on mass. That's how you say it doesn't matter in a formal way. It does not depend on or is independent of mass. What does it depend on? Well, it depends on, in the first one, it depends on g and theta, right? In the second one, it depends on g, theta, and mu. So you could say either one for your conclusion, what it doesn't depend on or what it does depend on. Any questions on that? So then if we want to try to apply it to this question here, it's the same question. It says it experiences no friction, right? So we just did one with no friction. So what's the acceleration of the box? We can just say A is equal to G sine theta, right? I yoinked it from above. This one's just a little bit more conceptual in that we can figure out sine theta. So the extra step we need to take here is if they give you the triangle, well, what is sine theta? We can just use this triangle to figure out sine theta. Sine theta is just opposite over hypotenuse, right? So in this case, we can just say A is equal to G times sine is opposite over hypotenuse, right? So 80 over 100. Or we can say A is equal to 0.8 G. And since acceleration is a vector, we need to give it a direction, right? So A is 0.8 G down the ramp. Yeah. And then for this speed stuff and the time it takes to go to the bottom of the ramp, that's where you're just going to use your kinematic equations. So I'm not going to worry too much about that. Okay, now we're going to have multiple systems, right? So on the physics test, they're going to say, draw a free body diagram here, maybe for the helicopter car system, right? So when they say blah, blah, blah system, we're going to look at just those two things, forget about everything else. And remember here that whenever you have some sort of rope or tension or something, that your arrows need to be equal and opposite. It's not possible in physics 1, at least. In the real world, yes, it's possible, but it's not possible on a rope for you to have tension greater on one side than on the other. That doesn't physically work in physics 1. When it says something's at rest, then each body itself needs to have equal and opposite vectors also. So this car is going to have an mg here, right? What do you think's pointing up on the helicopter then? We're gonna call it buoyant force. Right, buoyant force is anything that something's like in air or in water, right? It's the thing that pushes it up. So it's obviously its blades are spinning, right? So it's creating some sort of buoyant force to like keep it up. For number 6, just remember to pay attention to if this pulley has mass or not. So at this point where we are, we're assuming all our pulleys are massless, but once you get to torque and inertia, we're not gonna assume that anymore, because when your pulleys are massless, that means tensions are the same. When your pulleys have a mass, then you're gonna need to be like T1 and T2. But right now we're just assuming massless, right? So this would be just M1G maybe, FN1. And then it says this, the big block has friction, so this is FF. I'm just labeling this block 1. Okay, and then this one will be M2G. And I can't draw the arrows with the proper length here because I don't know which direction it's moving. Maybe there's not enough force to overcome static friction or not. Let's do this one with the TV guy. TV guy pushes TV. Guy doesn't touch the cart. The cart has frictionless bearings, meaning the wheels, right? The wheels on the bottom have no friction. So what do you think the free body diagram would be for the TV? And what do you think the free body diagram would be for the cart? I'll do the easy ones. The TV has mg pointing down. And then the cart has mg pointing down also. And since the cart is touching the ground, I'm going to say normal force. But since the TV is not touching the ground, I can't say normal force. So this one's also a question mark, actually.
Would the upward force on the TV also just be normal force?
We can't call it the normal force because we're only going to call it the normal force technically when it's touching the ground. I guess you could. They're not going to be that picky. But where's the force originated from?
Is it from the friction?
On the TV?
Yeah.
No. The upward force is from the cart, actually. Technically, it's a normal force from the cart. We'll just say the normal force from the cart. I'm being really picky right now. I don't think they're going to be that picky. Okay, what other forces are on the TV? A leftward or rightward? None? Both?
Is there friction on the left between the cart and the TV?
Good. The force of the friction between the cart and the TV. Cart on TV. Yep. Anything to the right?
Would it be applied force?
Applied force. And I'm for sure gonna make this one bigger, right? Because oh, let's clarify here. What do you think? Is it static friction or kinetic friction? If we had to assume. I know we shouldn't assume, but what should we assume? I'm assuming the guy's pushing the TV because he doesn't think the TV's going to slip, right? Imagine you just bought a brand new TV and you push it on a cart and it just falls apart. So we're going to assume that this is static friction. Yeah. What about the cart then?
Could you label it like we're doing the natural force? So could you do like force applied to the TV?
Force applied to the TV. This one's the applied to the TV, right? That one's applied to. I want to think of what the cart's feeling. So the cart feels the ground pushing up on it, right? So this is the normal force from the ground.
Would there be frictional force of the TV on the cart?
Which way?
To the right?
To the right. This is your equal and opposite. Force of static friction from the TV onto the cart. Any other forces on the cart? I was being really picky when Bobby was talking about the normal force of the cart, right? Because think about it. So now the cart, the TV is on top of the cart, right? So the TV is pushing down on the cart. The cart isn't falling apart, right? So if the cart's pushing up on the TV, that means the TV is also pushing down on the cart, right? That's your equal and opposite, right? Anytime there's a point of contact and within your system, right? This is our system right now. Oh, no, not the person. The person's not part of the system. Go away, person. Right? There's always going to be equal and opposite forces within the system, right? So there's one here and there's one here. These hands are just coming in out of nowhere, right? It doesn't feel it. So there's just one to the right from the person. And then the ground is not part of the system. So we just feel the ground by itself. The earth is not part of the system, right? And then we have the friction force here and we have the friction force here. Yeah. So within your system, your enclosed system, think about, okay, if there's something here that's kind of in the middle, if something's pushing down, then there must be an equal and opposite somehow. If something's going to the left, there must be something to the right somehow. Yeah. Questions on that? And then we have this pulley run, right? So this, again, we're going to assume massless pulley. So this one's not too bad if you remember. This T is the same as this T. And then now when we have a different like thing here, then we're going to have to label it, right? So then this one's going to be a T2, right? And this one's going to be a T2, equal and opposite. And then obviously everyone has a simple mass on it too. So I'll do this one pretty quickly. This one's T1. This one has a big mg. This one's M1, has a little M1g. And then T2. And then M2 has an M2g. It has a T2 pulling down also, right? And then it has a T1 pulling up. Okay, so that's your free body diagram there. I want to do the roller coaster one too, just because they love roller coasters on the AP exam. So remember that at any point, no matter where you are, right, we're assuming the Earth is a flat surface. So at every point on the roller coaster, you're always going to have the same mg pointing down, just as if something's flying through the air. We did that example earlier. And then here, we're going to figure out our normal force, right? Normal force is perpendicular to the surface. So for this one, Fn is going to be this way. Right, and for B, it's at the bottom of the track, so it's perpendicular to the surface down here. And then for C, if you're at the top of a loop-to-loop, the normal force is pushing the opposite way, right? It's pushing down. That will be for your roller coaster questions. Yes. Okay. So here's this concept check then. So here, I'm applying a torque to the wheel and the wheel's moving forward in the first one. And on the second one, I'm just pushing on the wheel so that it's gonna roll forward, but it's gonna slide on the floor. So this one's gonna not slide and it's just gonna roll. Okay, and this one's gonna slip. So think about it as rolling and just gonna, right? So it's gonna slip. So my question to you is, can you tell me where the friction is going to point on the first one and the second one? Which direction will the friction point on the first one, and which direction will the friction point on the second one?
Would the friction point on the left for the first one?
This way.
Yeah, counter or clockwise.
Counterclockwise. No, friction can't be clockwise or counterclockwise. Friction has to be a straight line. So are you saying you think it's going to point straight to the left?
Yeah.
What about the one on the right?
Would it still be left if it's slipping even?
So here's the concept, right? If it's slipping, right, that means its motion is going to want to go to the right. And remember the idea that friction is an opposing force. So the way the floor feels, right, is the floor feels that the wheel slipping to the right. So for sure on the one on the right, it's going to point to the left. This one's going to be more important for later chapters when you do torque and inertia. But imagine if the wheel is coming in contact with the ground and it's not slipping, that means there's going to be static friction. And when there is static friction, this is the idea of how friction can help a car speed up, right? When there's static friction and it's rolling, the direction of motion is actually going to be this way. The wheel's going to move this way and it's going to be pushed off the ground. And what is pushing in this case? It's going to be the force of friction. It's really hard to conceptualize, right? But you have to think the wheel is turning and it's hugging the ground. It's not slipping on the ground. And when it hugs the ground, look at my fingers. My fingers are digging into my palm, pointing to the left, right? So when it's pointing to the left, the ground is pushing my hand to the right then. So in both cases, the friction, the force is to the right, so the wheel moves to the right, yeah? But look, the friction here is helping it resist rotation versus here it resists the sliding. So please keep that in mind for later chapters when you do torque and inertia, right? If it's just slipping, just like a box you're pushing, that's easy to conceptualize, right? But when you're rolling something, like maybe do the thing, I just thought of digging my fingers in. It kind of helps me remember, right? It's pushing it forward. So the idea is friction can specifically speed you up, most likely when you're in a car and the wheels are on the ground. Yeah. Okay. So then we'll stop with a, I don't want this one, no. This one? No. This one? Let's do this one. This will be our AP review question. A block of mass M is set on a horizontal tabletop where the coefficient of friction is mu. A rope attached to the block passes over an ideal pulley. So ideal pulley means massless and hangs vertically. In case 1, a person applies a constant 98 Newton force to the rope. In case 2, a 10 kilogram mass is attached to the end of the rope. So where should you draw arrows for the block of mass M, and where should you draw arrows for the block of mass 10?
We could first like draw a force of gravity for the 10 kg block.
Okay. So how many boxes do you want to do? 3, 4, 5.
Is the 10 kg block pulling down on the, like, is it moving down? Like, is it heavier than just the block of mass M?
Let's see, is it heavier? We don't know yet. So it's just saying using longer arrows to represent stronger forces. So I don't know. So I think the two blocks will be independent of each other.
Yeah, that's what I was wondering because like I was gonna also say that we could put a tension force pointing upwards on the same 10-kilogram block, but
Yeah.
I'm not sure if that would, if like we should make it the same length
Good
as
question.
the
So let's
MG.
look at the let's look at part A again. It says the dots below represent M and 10 in case 2 after the system is released and while both blocks accelerate. So this should maybe answer your question. What do you think that tells you then if both blocks accelerate?
Then one of the forces is greater than the other.
Greater than the other, right? You can't have acceleration if they're the same. So which arrow is going to be bigger? If they're going to accelerate, where do you think they're going to accelerate?
Maybe downwards.
This one's going to go downward, right?
Yeah,
Yeah. So then which arrow is going to be longer?
the MG.
The MG arrow. So it doesn't matter how many you choose, right? So maybe 4, right? And then maybe this one, because we don't have enough answers yet. So maybe make this one 3. So then there you go, mg, right? So 10g maybe, or mg, and then this is going to be force of tension. So then how will that relate to block of mass m then?
Maybe the block of mass M will have like a rightward force of the MG force of the 10-kilogram block.
Not the mg, say, try again.
Tension.
Tension, right? Because tension is the same rope, same string. So actually that one we can steal then, right? If I made this one 3 blocks wide, I should make this 3 blocks wide then. Right, so that's going to be the tension there. Does block M have any other forces on it?
It has a force to the left of it's just force of friction, so like mu mg or something.
How
like
many
that.
squares should we make that?
I'd say like 2.
Less, right? We want it to be less because if it's equal or more, then it's not going to accelerate. So there you go. That's FF. Any other ones?
There's also normal force and gravitational force.
And then that one, we have no clue how much it is. So we're just going to give it some random. I'm just going to do 2 and 2 because I don't know. As long as they're equal, that's all that matters, right? So this is where it's important to know the length of everything. You don't need to know the exact length. You just need to know how they relate to each other. Cool. Okay. And now this case, right? So in which case does the block of mass M have greater acceleration? Is it the first case? Is it the second case? Or is it both?
If we assume gravitational force is 9.8, wouldn't it be both?
Yeah. Right, and then now you just have to write in a coherent sentence, right? If we assume that the acceleration due to gravity is 9.8, then both the 98 Newton force and the weight of the 10-kilogram block would equal. And assuming that it's the same table, then they would both have equal accelerations. And you just write using 2 or 3 full sentences. Cool. Any questions? Okay. So then this weekend will be your first foray into practice testing. I have it set for, when do I have it set for? I have it set for Saturday at 1. Just so you're aware, you know, they changed the tests so that they're not going to have the electromagnetism part and the waves part. Obviously, I don't have any tests that have those, so I'm going to give you ones that have the electromagnetism and waves. So if you don't know how to do it, it's okay to skip it. I'm going to add some extra questions that are related, but don't freak out when you see that. Cool. Any questions?
Will you be releasing like the filled out form of what we did today with like your writing over it again? So you did that last week
Yeah.
session.
Yeah.
Okay.
Alrighty. All right. I'll see you all next time.
Thank you.
Thank you.
Goodbye.